Awesome.
Did you see I
Yeah.
started? Okay,
Yep.
that's
Yep. Right.
yes. Okay, so let me do a brief introduction before you actually start this
Sure. Yeah.
process. Uh, Hello, everybody. Today, we're really happy to have Sadovik from UW Madison to give us a talk today. So, Sadovik is a fourth year doctoral student at University of Wisconsin-Madison. He works at the intersection of computer architecture and quantum computing. His work has appeared at architecture conferences ISCA and Micro. Uh, Sadovik has won the Hiram Mayok Award and is an alumnus of the Heidelberg Laureate Forum. Prior to grad school, he worked as a protocol transactor developer at Synopsys. Okay, take it over, all yours.
Great. Awesome. Thanks, Dee. Uh, yeah. Thank you, everyone, for attending the talk. And today I'll be talking about um, quantum computing and the control hardware required for quantum computers and how we can make that control hardware more scalable. So here is an outline of the talk. So I'll start with a brief, 101 on quantum computing for those who are unfamiliar with the field. And of course, I'll also talk about quantum control and what it implies for quantum computers. And then I'll move on to quantum error correction, which is the meat of this talk. And in particular, I will talk about how we can make the classical processing required for implementing quantum error correction cheaper by using virtualized decoders. All right, so let's get started. Quantum computing, we can consider quantum computers to be, well, in the future, maybe not now, but in the future, they can be thought of as domain-specific accelerators. So something like, how a GPU is for machine learning these days, or historically for graphics. So if anyone tells you that, when am I, when should I expect a quantum computer in my phone? They don't know what they're talking about. It's not going to happen. Quantum computers are going to be used for very specific applications. And the fundamental unit of information in a quantum computer is a qubit, a quantum bit. And this is analogous to how, CPUs and all classical hardware have bits. So that's the analogy I'm using. So now, in recent years, quantum computing has, of course, been kind of a buzzword, and there has been a lot of investment in this field. So here are some, but not all. These are some chips and some quantum computers that have been developed by Google, IBM. QEra is a new startup out of Harvard. And what we're seeing is an increase in the number of physical qubits. Um, Now, this is expected to continue. All these companies have their own roadmaps about what they want to do. So we will see more investment, more progress as far as the number of qubits goes, as far as the complexity of the system goes in the next five, 5 or so years. So now coming to control hardware, what is it? So we can consider it to be like the middleman between the classical computer, where a user would be writing their quantum algorithms, basically the quantum software. Um, this quantum software needs to be translated into language that the physical qubits, which you see on the right, can understand. And so the control hardware acts like an intermediary. It allows the interaction of the classical world with the quantum world. So that kind of answers the question automatically about why it's important, because any user application, any circuit, any algorithm that you want to implement using qubits, they first need to be translated by the control hardware. And so it acts like a bridge between what we understand as humans. We are predominantly classical. Our understandings are, we work on a classical scale, right? And so the control hardware is kind of like the bridge between the software, which is us and our applications, and the quantum devices themselves. So at present, quantum control and quantum control hardware is really complex, and it's very ad hoc at the moment. And a lot of brute force, scaling techniques, a lot of brute force methods are being used to just control a certain number of qubits. So as an example, I've got a picture here that shows the control hardware for the Google Sycamore processor. This is from 2019. I'm sure it's even more complicated now. But basically, this is one rack of their control hardware. They had four such racks. And the table on the right just shows you the number of discrete components required for controlling just 53 qubits. So it's a lot of hardware that you need. And so, of course, if we want to make this more scalable, what we would like to do is maximize the number of qubits we control per controller. Now, the controller could be one board, it could be one rack. That doesn't matter, but we want to maximize the number of qubits we control per discrete hardware component. And of course, there are multiple ways you can do this. So radio frequency system on chips. These are SoCs built by Xilinx, and they are really nice because they integrate CPUs, FPGAs, and all the digital to analog to digital components onto one chip. And so a lot of people are starting to use or like exploring how to use these RF SoCs for controlling qubits. And of course, if that doesn't work out, and it maybe won't, we have ASICs. We can just fabricate our own control chips, really dense integration, and that should be able to maximize the number of qubits you control per controller. In fact, IBM at the moment is working on cryogenic ASICs, where they would put this ASIC controller chip very close to the qubits at around 4 Kelvin. So yeah, that's the kind of research being done in this particular field. So now I'll talk about a couple of things that I've done just to make this control hardware more scalable for superconducting qubits, and that's why I call it technology-specific optimizations. All these optimizations may or may not be applicable for other qubit technologies. So for superconducting qubits, if we wanted to implement something like an X gate, which just flips the state of a qubit from 0 to 1 or 1 to 0, the control hardware actually synthesizes that as a high frequency microwave pulse, which you see between the control hardware and the qubits. Um, Now, this microwave pulse is actually stored, or the envelope of it is stored in a structure known as the waveform memory in the control hardware. As in when you perform a gate, this waveform memory is read and the envelope is passed to the digital to analog converter. You do some signal mixing and you get this final microwave signal. Now, what we worked on was actually making this waveform memory more scalable because we saw that if we increase the number of qubits per controller, the bandwidth and capacity can be an issue for FPGA or ASIC controllers. And so we came up with this scheme of compressing waveforms and decompressing them at runtime. And this allowed us to control 5 times more qubits per controller. The next technology-specific optimization that I worked on was on readout. And the readout is the reverse process where we're trying to read the state of a qubit. So the readout signal passes through an analog to digital converter, which produces a time-dependent signal, which you see on the GIF on the bottom right. Um, Now you can see that it's different for states 0 and state 1. And so we pass this information through a classifier that gives us the qubit state, whether it's in state 0 or state 1. Now, this is essentially three-dimensional data that we're working with. So what we can do is filter it, and that gives us these nice clouds. And we can easily, distinguish between state 0 and state 1. You can see there's like a very clear linear boundary between the two states. And you can use very simple heuristics to discriminate the state of the qubit. Now, this is a very this is a very clean image I'm showing you. It's not the reality. The reality looks like that. A lot of the measurements corresponding to state one end up in this cloud occupied by state zero, and this actually makes your readout or measurement accuracy very low. And these happen because when you prepare a qubit in state one, it has a tendency to kind of just relax back to state zero. You give it a lot of energy, it loses that energy over time, and it relaxes back to state zero. Um, so in this particular work, our key insight was that we can actually identify these transitions when a qubit is going from state one to state zero. And so here I've got the red trace that you see, which is basically showing that transition when a qubit goes from state one to state zero. This insight actually allowed us to create a better classifier, which used a very small neural network. And by using the small neural network and by using this and by using a pattern matching algorithm to kind of detect these one to zero transitions, we could improve the accuracy by improve the accuracy significantly while using very minimal FPGA resources. So this made our classifier very scalable and also very accurate. Um, I can take questions in between, but if it's on the chat, I think it's better if I take it towards the end of the talk. But if you have something like a burning question, please feel free to interrupt me at any point during the talk. Um, all right. So having discussed all of these things, let's now actually move to what I really want to talk about, and which is just higher control abstractions. So far we've looked at very low-level control stuff. So basically, microwave pulses and readout signals that you receive from the qubits, and then you perform some kind of computation on them. Above this low-level control, there is another abstraction of control that we can consider for scalability of quantum computing systems. So to get there, I'll first introduce the problem and the notion of quantum error correction. So qubits are expected to have a 0.1% chance of error per operation. Now, we're not there yet. This number is probably 0.5 or maybe 2% right now, depending on who you talk to. But the goal is to get to somewhere close to 0.1% chance of error per operation. So any operation that you do, there's a 0.1% chance that it fails. Now, if you compare this with a very classical component like a DRAM stick, the failure rate is significantly lower. It's orders of magnitude lower. So for a DRAM stick, it could be anything between 10 to 100 failures per billion device hours. So that's a really low chance of error per operation if you try to translate the numbers. And so the key question that has been answered, it's not a new question that I'm asking, but basically it's can we introduce some kind of redundancy, some kind of error checking, error detection mechanism to make these qubit lifetimes, to make the qubit um, error probabilities better. And that is the whole field of quantum error correction. How do we do this? How do we make qubits? A single qubit might be very erroneous, but can we actually introduce redundancies into the system to make maybe a bunch of qubits more resilient to errors? So a brief digression on this topic. So when I started around 4 years ago on this, like just working on, computer architecture and quantum computing, quantum error correction was a very abstract topic for me. It was very theoretical. People yeah, no one really knew whether it would actually work. And it's been really nice to see that over the past 2 years, there have been multiple experimental demonstrations showing that quantum error correction does indeed work and that it is the correct way to move forward as far as fault-tolerant quantum computing goes. And we need fault-tolerant quantum computing in order to run algorithms that are actually useful, and algorithms that can actually benefit from a quantum computer. So yeah, that was a brief digression. So now let's get into the weeds about quantum error correction. So we start with a single noisy physical qubit. So it could be very erroneous. It could have an error probability of, let's say, 0.1% per operation. We take a bunch of these noisy physical qubits, and then we encode them. And this encoding basically encodes all these physical qubits into one logical qubit. The code distance is something even classical coding theory people use. The distance is basically a measure of how many errors, or it's an indicator of how many errors a particular logical qubit can tolerate. Um, so once we've done this encoding, we have a logical qubit, and our hope is that this logical qubit actually survives longer and is more resilient to errors than all these, individual physical qubits. So now this encoding can be performed using a variety of error correcting codes. So there are these quantum error correction codes like the surface code, QLDPC codes, there's also color codes, and basically, you can use any of these codes. Of course, there are a lot of factors, but you can use any of these codes to encode these logical qubits using a lot of physical qubits. So how does this encoding work? So what we do is we divide all these physical qubits into two groups. We call one of the groups parity qubits. So these are the qubits we actually measure repeatedly in order to detect errors. And the remaining qubits are what we generally call data qubits. So we execute a sequence of gates. So just, a fixed sequence of operations. And this is highly dependent on the error correcting code that you're using. After we execute these gates, we measure all the parity qubits. And when we measure these parity qubits, we get syndromes. And these syndromes are actually what we use to detect and correct errors that happened in that lattice of physical qubits. Um, by doing this repeatedly, what we can ensure is that the state of the logical qubit is preserved, even if the constituent physical qubits incur errors repeatedly. And of course, there is a certain limit to how many errors and how many errors we can detect or correct, and that is dependent on the code you use and the distance you use. But this is the whole notion of quantum error correction. So moving on to syndrome generation circuits, they're important, but they're not very interesting for, computer architects. So let's move to like the real, the interesting parts of this entire cycle, which is basically this error detection and correction aspect of quantum error correction. So again, we did some operations on all these physical qubits. We measured the syndromes, and we keep measuring them. And we use these syndromes for error detection and correction. And this is performed by a decoder. Now, the decoder's job is very simple, but also very hard. And it's basically given a set of syndromes, the decoder must identify what errors happened and where they happened across all those physical qubits. And these decoding algorithms are entirely classical, and people have and people will be implementing them on FPGAs or ASICs, and they, of course, have been implemented in software, and you can use software decoders, but there is a problem with that. So we will be focusing on decoders for the rest of this talk. So now coming to these decoders, let's say the time taken to measure one set of syndromes is the cycle time of your quantum error correction code. So this is the syndrome generation cycle. Let's say the time taken by the decoder to decode these syndromes is T decoder. Now, a necessary condition for universal error-corrected universal fault-tolerant quantum computing is that the time taken by the decoder must be less than the time it takes for you to generate one set of syndromes. And very simply, this is a simple, queuing theory problem where you are receiving syndromes from this queue of basically the queue being all your physical qubits. You are processing these syndromes, the decoder is processing these syndromes. So the rate of processing must be greater than the rate of syndrome generation. And this is a necessary condition. And this constraint, this latency constraint on the decoder has actually prompted a lot of architectural research on accelerated hardware decoders for quantum error correction. And so these are, some papers that I've cited that have appeared at ISCA, HPCA, ASPOS. And these are all decoders that try to get better latency, sometimes at the cost of accuracy. And that's been the focus of all prior work. And it's important, it's great, but our work, or like the work that I will be talking about today, is slightly different. So people have focused on designing these decoders, have designed on, making these decoders faster, sometimes at the cost of decoding accuracy. But I will be looking at it from maybe a slightly higher abstraction. And the key question that I want to kind of answer is, if we have a bunch of logical qubits in our system, do we need a decoder? Do we need this accelerated decoder for every logical qubit in the system? Now, what we found while answering this question is that there is a trade-off between the memory required for storing syndromes, for storing the syndromes that you can't process at a particular point of time, and the compute you need to actually decode all the errors that happen. So this is kind of like a graph that I'm starting to show you, which is basically a trade-off between memory and the compute you need. So if we have, if the number of decoders is equal to the number of logical qubits, this is great because now every logical qubit can just send its syndromes to a decoder, to its own decoder, and the decoder can work on it. And assuming the decoder is fast enough, we will never need to, store an unnecessary amount of syndromes. But what if let's say these decoders are far less than the number of logical qubits in the system? What we found is that the memory requirements for storing all the syndromes that you haven't yet decoded, those memory requirements actually grow exponentially. And we want to avoid this exponential cost in memory because, yeah, we might not have enough memory to store all those syndromes. We might not be able to store all those syndromes in memory. So the goal that we set for ourselves was to reduce the number of compute resources needed, while also not requiring an exponential amount of memory compared to the case where every logical qubit in the system has a decoder. So if we want to visualize this, so the case where every logical qubit has a decoder is the image on the left, where every qubit is connected to a decoder D. If we don't have decoders for every logical qubit, you would probably see an image that looks like the image on the right, where basically some decoders are being shared among logical qubits. So it's kind of like a time division multiplexing of decoders between logical qubits. Now, how you allocate a decoder to a qubit is very similar to, very traditional operating systems where, you have a lot of processors, you have a limited number of CPUs in your system, and you want to construct a scheduling policy that allocates processes to all those CPUs. So the CPU scheduling policy is a very good parallel to what I'm trying to explain here, which is we have a fixed number of decoders in our system. We have more logical qubits, and we want to find a way of allocating the syndromes generated by these logical qubits to those hardware decoders in the system. And we want to do this optimally. If we don't do it optimally, this is the kind of data that we saw. So here, what I've basically done is I've taken a workload. I've taken the benchmark is called W state 60. It's got 60 qubits in the original benchmark. And on the x-axis, I've got the number of quantum error correction rounds. So in every quantum error correction round, you produce, some amount of bits, which are basically your syndromes. On the y-axis, I've got the memory required to store all the undecoded syndromes. And what I did was just vary the number of decoders that are present in the system. So starting at, number of decoders equal to 200, which is basically I'm giving every possible logical qubit a decoder for itself. We don't really need any memory. You know, we don't need any memory, and that's the green dash dot line that you see. But if we start reducing the number of decoders, we see that after a point, the memory required just starts growing exponentially. And it is this exponential growth in memory that we want to kind of avoid. Now, you might say that 160 gigabytes of memory it's not a lot. Like, we have servers, we have GPUs that need this amount of memory, and that's not a big problem. But I would like to say that this is a very small benchmark. For quantum error correction, we will be running larger workloads. We don't know what those workloads are, and that's, I think, the biggest criticism of quantum computing at the moment, that we don't know what we can use a quantum computer for. But it is it's certain that the workloads that you will eventually use on a fault-tolerant, on an error-corrected quantum computer would be much larger than this W state 60 benchmark that I'm showing. So the memory requirements would likely be much, much higher. And so it is important for us to kind of come up with a scheduling policy that ensures that this memory requirement is manageable and that it doesn't grow exponentially. So I'll jump straight to the key insight, which enabled us to kind of solve this problem. So the image on the left again is showing you how, if you change the number of decoders, if you reduce the number of decoders, you have to start doing kind of like a time division multiplexing of those decoders with all the logical qubits. And what we found is that the key of reducing this memory requirement and for also speeding up things as far as decoding is concerned is actually reducing the number of rounds for which a logical qubit remains undecoded. So the image on the right shows you two logical qubits, Q0 and Q1. And Q1 is actually remains undecoded for, let's say, 6 time slices. And what we want to do is ensure that this is the minimum amount, or like this duration for which a logical qubit is undecoded is minimized. And there was quantitative evidence suggesting that we should do this. And this graph on the left is kind of showing you why. So here, all I've done is I've left a qubit undecoded for a certain number of error correction rounds. So that's the x-axis. So D, 5D, 10D, and so on. And then I compute the decoder latency normalized per round. And we see that it's almost exponential. The decoding latency per round increases almost exponentially as you increase the number of rounds for which you leave a qubit undecoded. And this is highly undesirable. And so what we want to do is ensure that every qubit is decoded very frequently so that the longest undecoded sequence is minimized. And so that's the key question. How do we schedule decoding such that we minimize this sequence length of the longest undecoded qubit? So I'll quickly walk you through some decoding scheduling policies that you could use. So the first is MFD. This stands for most frequently decoded. And so the example setting. So this is like a very small toy example that I'm working with. We have three logical qubits that are undecoded. We have a logical qubit that needs to be decoded. So that's the decoded. That's the logical qubit that's in the color blue. And we only have two decoders available. So how do we schedule decoding among all these three logical qubits when we only have two logical qubits remaining? So the MFD policy sorts all these logical qubits that are undecoded on the basis of, which logical qubit is consuming the most number of non-Clifford gates. And this is important. I haven't really talked about it, but this is important because these are the logical qubits that really need frequent decoding. And after I create this kind of sorted list, so I've basically ranked all the logical qubits in the order of, the number of non-Clifford gates that they consume. I can schedule decoding for, the first n, in this case, the first two logical qubits of this sorted list of logical qubits. The second policy is something we've seen in operating systems, which is a simple round robin policy. So now we have three logical qubits that are undecoded. We select the first two. We schedule decoding for those at this particular time step t. And the next time step, we schedule decoding for the next two logical qubits. And so this kind of ensures fairness across all logical qubits. The third is MLS, which I call the minimizing longest undecoded sequence length. So here we again sort it, but this time we sort it in the order of which qubit has remained undecoded for the longest period of time. And the logical qubit which has been undecoded for the longest period is at the top, and we schedule decoding for that logical qubit. So this ensures that we are constantly minimizing the longest undecoded sequence length for any particular benchmark. And now, having kind of quickly gone through all these scheduling policies, here are the research questions that I want to kind of answer. So the first is, how many decoders can be virtualized? And if we do virtualize these decoders, how long will these logical qubits remain undecoded? And if we do virtualize these decoders, what are the memory requirements for storing all the syndromes that are yet to be decoded? So we took a very workload-centric approach for this. So we use these benchmarks, and the the rationale for using most of these benchmarks was that these, except maybe QAOA, all these benchmarks represent building blocks for larger quantum algorithms. And so this would be a good representative of, what would be running on an actual fault-tolerant quantum computer. And the methodology we used was to use a compiler, which is called the lattice surgery compiler. So we focused on the surface codes, we focused on lattice surgery-based computations, and we passed these benchmarks through the compiler to generate an intermediate representation of all the operations that you would need to actually execute that benchmark on an error-corrected quantum computer. And then we used this intermediate representation along with a resource estimation tool provided by Microsoft Azure to actually compute and memory estimates for all these different benchmarks. All right, so let's look at some statistics. So here are all the benchmarks on the x-axis and all the logical qubits that these benchmarks would need on the y-axis. So these aren't, big benchmarks, but they do require about 100 logical qubits and W state 60 is actually the largest one, but anything between 60 to 100 logical qubits are required for all these benchmarks. Um, Next, we look at the number of t-states. I have not talked about t-states, and that's by design because I don't really want to confuse anyone, but t-states are important for universal error-corrected computers. And these are just a measure. So this graph is just a measure of, how many T states you need to implement a particular algorithm. And these actually are really important for decoders. Um, and then the final thing, which is just an estimate on the number of FPGAs you would need for decoding. Now, I have two bars for every benchmark. The first is single, which basically means that I only have one magic state distillation factory, and the other is optimal, where, I'm trying to optimize the number of magic state distillation factories in order to produce a necessary amount of T states. And sure, these aren't a lot of FPGAs, but again, these benchmarks are kind of tiny compared to what you would actually run on a quantum computer. And what we want to do is actually minimize the number of hardware resources that we need. So after we virtualize everything, after we use the MLS policy, this is kind of like the data that I generated for all these different benchmarks. So the second column is the number of decoders that you would need for if you were to supply a decoder for every logical qubit. Now, if we did do virtualization, if we used a scheduling policy that was actually really good, we can actually reduce the number of decoders significantly. So what we see here is by using virtualization, we can reduce the number of hardware decoders required by up to 18x. So that's a big reduction in the number of hardware decoders that you need. And this will obviously translate into the number of FPGAs or the number of ASICs that you need for actually implementing those decoders in hardware. Um, so this is like an overview of the results, but why does this happen? So let's look at the longest period for which syndrome remains undecoded. And here I have all the three scheduling policies that I introduced earlier. And the MFD policy is terrible because it basically ensures that some logical qubits always get decoded while others are actually starved of decoding. So as a result, the MFD policy actually incurs or actually results in very long undecoded sequences. And this, as you'll see in the next slide, this actually translates to higher memory requirements. Um, Now, the MLS policy, on the other hand, because we're actively trying to reduce or minimize the longest undecoded sequence length, the longest period or the longest number of time slices for which a qubit remains undecoded is quite low for the MLS policy across all benchmarks. And this directly um, correlates to a reduction in the memory requirements. So here I have the peak memory requirements on the y-axis. So the memory required to store undecoded syndromes. And on the x-axis, we have all the benchmarks. So because the MFD policy does a terrible job of kind of reducing the undecoded sequence lengths, the peak memory requirements are orders of magnitude higher as compared to the MLS policy, which is around the 100 megabytes, so 10 to the power 2 um, mark. So um, by using an optimal scheduling policy, which is the MLS policy in this case, we were able to reduce the memory requirements for all these workloads and also reduce the number of decoders that we need for implementing quantum error correction on the system. So what's the takeaway of all of this? You remember this graph from earlier? If we reduce the number of decoders, the memory requirements started increasing exponentially. Um, this exponential increase in the memory requirements can actually be mitigated and can be actually avoided by using a very optimal scheduling policy. And this is the key takeaway of all that I've talked about today. And to summarize, I have introduced how quantum error correction requires accelerated decoding to meet the strict latency requirements. And if we provide a logical qubit, a decoder, we would incur a very large cost in classical processing, and we want to reduce this cost. And so to do that, we introduced the notion of virtualized decoders, where logical qubits now share decoders. How they share decoders was basically the scheduling policy that I introduced, so the MLS policy, as I called it. Um, that determines how logical qubits actually send their syndromes to a particular hardware decoder and which logical qubits don't. And with this scheduling policy, we were actually able to reduce the number of hardware decoders by up to 18x and at the same time not require a ton of memory. And we were able to get away with just 100 megabytes of memory as compared to, let's say, 160 gigabytes. So um, that's all I wanted to talk about today. I know I've like finished early, but I guess this leaves us with more time for questions. And I'll be happy to take any questions. Thank you.
Okay, cool. Thank you, Patrick, for the wonderful talk.
Can't hear you, Lee. Sorry.
Yeah, so questions. I think we have a question previously in the chat by Pablo. The question is, I'm not sure about the question specifically, but it's saying I thought it had three states of memory per bit. So I guess is it asking how many bit per qubit in the per quantum qubit
So,
or
I
the
think
memory bit?
uh, you cut off in the middle. Could you like repeat the question? Sorry, I didn't hear the
Yeah,
entire question.
the full question is I thought it had three states of memory per bit. So I guess this question is more of a how the quantum memory is organized, right?
Oh, I see. Um, so three states would be a qubit, which is basically you have state zero, state one, and then also state two. Um, the thing is, even qubits do have a third state, but that's out of the computational basis. So when we design qubits, we actually want to ensure that all your computations are within this computational basis of state zero and state one. So these are the only two states that we want to work with. If the qubit does go into, like if you design a qubit, but it ends up going into the third state, then that actually breaks your computation down. It's actually called leakage. And it's actually a big problem for all these quantum error correcting codes because qubits do tend to go into the third state very briefly, but even a brief, excitation into the third computational state would basically destroy all the information that you have. So a qubit by design must have two states, but that doesn't mean that you can't excite it to a third or even a fourth state. Like there are actually infinite states, but you restrict the computational basis to only two states. I hope that that answers the question.
Okay, sounds great. Yeah, then I have a few questions for you.
Sure,
So
yeah.
yeah, I heard you're saying when you decrease the number of qubit, the cost of the memory overhead. Oh, sorry, decrease the number of decoders.
Decoders.
Yeah, the memory overhead increase exponentially. But from the graph, what I saw is it seems it's linearly, right? If you have a certain decoder count,
Let
I mean
me
the
get back
graph,
there.
the,
This
yeah, this
graph,
graph is the x-axis is
log.
log. Yeah,
Yes.
so how could you could you explain a bit why in which
Yeah.
dimension it's exponential?
In which dimension?
Yes, for
Oh,
example, is it along the number of measured rounds or number of decoders?
it's along the number of measured rounds. Yeah, because you're looking at the memory requirements, as you go through your computation, you require a certain number of rounds to complete that computation. Now, over here, like if you see between, oh, where's my, yeah. Um, so between this point, which is a little after, or this would be 11, 11 or 10,000? No,
Mhm.
2000 D. And between 2000 D and 3000 or 4000D, the memory has shot up by quite a lot. So that's the exponential increase that I'm talking about.
Okay, okay,
Uh, yeah, yeah.
okay. Sounds good. Yeah, then my next question is, have you count the multi-shot measurement? I know, for example, for surface code, if you're using the kind of a matching based decoders, you have to measure multiple rounds, and the number
Yes,
of rounds you need to measure is identical to the distance, right? So
yes.
in that case, how does that impact the memory requirement, and how does that impact the time of the cycle and the time of the decoder? You have to measure
Yeah,
multiple time to and then perform one decoding process, right?
right, right, right. Um, so yeah, I think I can clarify this using this figure. So you see this image on the right, right, where you have qubit 0, qubit 1.
Mhm.
Each square actually represents D rounds worth of syndrome measurement cycles.
Ah, I see.
Yeah,
So
yeah.
it's one complete
Yes,
decoding process.
yes, yes. And that's how you can actually kind of separate, the chunks of, syndrome generation cycles. So I didn't really get into like, every syndrome generation cycle. Instead, I treated it as a block of D syndrome generation cycles. So every square is a block of D syndrome generation cycles, and this blue square just represents that I've sent this block of syndrome generation cycles, or this block of syndromes to the decoder, and the green one is that, this block now needs to be stored in memory rather than get decoded.
I see, I see.
Yeah.
Yeah, that sounds cool. And yeah, then I'm not sure, maybe others also have questions, but I have my probably last question on my side. So um when you're using the longest undecoded sequence, so it definitely shows significant benefit in terms of number of decoders and a number of amount of memory you need. So
Mhm.
do you know how does it impact the decoding accuracy? For example, if you show the most frequent decoded scheduling, that one might create relatively longer undecoded sequence. So
Yeah.
that might have impact on the accuracy, right?
Yes. That's a good question, and I don't have any data that, compares the two. All I can show you is this graph on the left, which is basically showing how well, this is just decoder latency. So maybe not this graph. No, you're right. But actually, if you decode more syndromes at a time, the decoder accuracy would be better, but it would be slower.
I see.
Yeah.
So
Um, so the rationale behind it, so this is something called, like, this is the difference between a global decoder and a local decoder. A local decoder would be working on, let's say D rounds or 2D rounds at a time. A global decoder would be where, you run all your syndromes, you store all of them, and then you decode all the syndromes together. That would be the global decoder. And it has been shown that the global decoder is actually better than the local decoder. Um, so when you have a long sequence of undecoded syndromes and you decode them all together, it's actually likely that the decoding accuracy for that would be better. But as this graph shows you, the decoder performance would suffer. Like, it would get really slow, because the latency per round would increase as you increase the number of rounds that you're trying to decode.
right. So
So
in
that's
that
the trade-off.
yeah,
That's the
yeah,
trade-off.
I see, I see. So in that
Yeah.
case, where do you think the kind of single shot decoders could help?
Um, I think that's dependent on, like, the code. Like, for the surface code, if you introduce measurement errors and all those things, single shot decoding is probably hard to do. Uh, Simply because, you need at least, maybe 3 or 4 rounds to actually account for measurement errors that happen. Um, But yeah, it's an interesting question. Like, there are a lot of, like, decoding algorithms and, things related to decoders that we haven't actually incorporated into the study. Like, We've considered like a simple matching-based decoder for the surface code and like lattice surgery-based computation. That's all we've done. But yeah, I think there are like a lot of additional um, embellishments that we can add to kind of like make this more comprehensive.
Okay, sounds great. Yeah, so then we in the chat we have another question from Pablo. The question is the cost of energy of the equipment to read the quantum memory. Is it higher than a normal method? So I guess that's comparing to a normal memory.
Um, so by quantum memory, you mean like,
I think that's probably the readout process. The readout of a quantum computers is more costly than a classical one.
yes, it is because it requires a lot of a lot of discrete components. So if I can move to this slide. So this readout signal, it's actually coming from the qubits, and then you have to digitize it, and then this time dependent signal is what you actually use to like do state discrimination. Um, but simply because I haven't shown it here, but between the qubits and this, analog to digital converter, you actually have a ton of um, amplifiers, like low noise amplifiers, to kind of boost the readout signal so that it reaches, your room temperature control electronics. So it's actually a very costly process, and it's also one of the most error-prone operations in uh, superconducting qubit-based quantum computers, which is actually what motivated us to look at this problem. But yeah, reading a qubit is hard. Uh, that's all I can say.
Sounds good. Yeah, so any other questions from the audience?
Yeah, I have a question as well. Like for your scheduling policy, is like what you're talking about one single qubit that matching with one data qubit. But for example, in surface code, sometimes single qubits shared by like three or four data qubits, and one data qubit also shared by also need to measure by three or four single qubit. In this case, like we need to have a and data qubit matching with a certain number of single qubits. So in this case, would the set schedule policy also works?
Um, so are you talking about like how one logical qubit has data qubits, measure qubits, and like, every data qubit is, or every measure qubit is connected to four data qubits?
Yeah.
And well, what we've done is actually we've abstracted all of that away.
Okay.
So what we're seeing here is actually the full logical qubit. It could be, any distance. It could be d equal to 3. It could be d equal to 15. That doesn't matter. All we're saying is that, we are receiving syndromes from these qubits. And the syndromes would be from the measurements of all the measure qubits in that, lattice, right?
Yeah.
Um, yeah, so we're just saying that we're receiving those syndromes and we are kind of scheduling the decoding for a particular logical qubit syndromes at a particular point of time. That's all we're doing. We're not really going into a logical qubit and changing the scheduling within the logical qubit, if that makes sense.
Okay. I get it. Thanks.
Yeah,
Okay,
thanks for the
cool.
question.
Yeah, then any other question? Probably you have time for the last one, if any. Okay, if no question, let's thank Sadovik for the last time. Ooh, thank you for spending your time with us and share with us your cool work on the corner attraction. So yeah, so
Yeah,
thank you. I think that's
thanks
all
for
for
having
today.
me. Yeah,
Yeah,
thanks for
no
having me.
problem.
Yeah, and thanks for attending.
Anytime.
Yeah,
So
yeah,
yeah, then I think that's the end of today. So uh that's it.
yeah.
So see
Okay.
you all next time. Take care.
Yeah. Pablo, I'm happy to answer questions over email, or if you want to like, have a Zoom call or something.
Sure.
I'll be happy to answer questions.
Yeah, yeah. One last thing. I'm gonna share your video to the YouTube and also probably also share your contact with the audiences. I mean, to our Compact student list so that people can reach out to you if they're interested. Okay.
Awesome. Yeah, yeah, yeah. That sounds great. Thank you.
Okay.
Yeah,
Sounds great. Thank you.
awesome.
See you
Yeah.
next time.
Bye-bye.
Bye.
Yeah, bye.